three-dimensional vectors, we will have to draw the axis correctly all the time. So here, I would have to draw three axes, x, y, z. And I know we always drew, the y-axis vertically, right, and x-axis horizontally, but we're going to have a slight difference here. Notice I did not label these axes yet. However, I will. Whoa, what is that? Well, this is your positive x-axis that's coming straight at you like this. Well, not at you, but sort of towards you. This axis going to the right is your positive y-axis. And going straight up is your positive z-axis, okay? That makes this negative x. This is your negative y, and this is your negative z. Is everybody okay with that so far? I don't know if you could see it, but this angle here, from the positive x-axis to your y, positive y-axis, this is actually a right angle. And positive x and positive y would make first quadrant, quadrant 1. So this whole thing here is quadrant 1. This is your 0 degrees, and it will be measured this way, counterclockwise, where this is 90 degrees, and this is 180 degrees, and this is 270 degrees, and back to 360. Okay? Then, this right here, even though this looks a lot less than 90 degrees, it is actually 90 degrees. This is 90 degrees. And this here, right, all this here, will be your quadrant 2. And then this here is also 90 degrees. So all this will be quadrant 3. And then this is also 90 degrees. And this is quadrant 4. So all this will be quadrant 4. So it would create a plane cutting through, right? This z-axis will cut through the plane at 0, 0, 0. So this would be 0, 0, 0. So this plane of xy plane is going through z-axis at 0. Does that make sense, everybody? All right. So if you want to visualize this more physically, do this. Draw an XY axis like you always draw. Here is your X, right? Here is your Y. Right? And then, ready? I wish I had a thinner line. If you were to do this, right? If you were to do this, you're sort of looking at your z-axis coming through that 0, 0. Whoa! Right? So your z-axis is actually, this pen going through your xy plane where z is at 0. Sort of like, you're sort of looking at it like this, I guess, like that. Is what this is doing. All right? So this will be the first quadrant, right? Quadrant 1. And this would be the quadrant 2, right? This would be the quadrant 2. Notice how these are all perpendicular. And this would be quadrant 3, right? And this would be the quadrant 4. And that's what you will see. It's sort of like that. So your x-axis is coming this way, your y is going that way. It's sort of skewed like this. Okay? Is everybody okay with that? Then, let's draw a vector r. So here, I'm going to draw a vector r that has Rx x hat, I guess. Maybe I should get rid of that. Rx plus, right? Ry, y hat, and then Rz. All right. And let's say they are all in positive, positive, positive. So it's going to be in first quadrant above the xy plane. Okay? So Rx will be drawn on the x-axis, at least parallel to it. Right? So this will be my, let's make it a little bit bigger. Here's my Rx. This is my Rx vector. Here's my Ry. This is my Ry vector, which is this. And my Rz vector, which is the z component of my R, position R. This is my Rz vector. This is my position vector R. So that's my position vector R. If I were to cast the shadow of my R vector onto my xy plane, the shadow of this R vector would be from the origin to the ry. So this is the shadow vector of my r. This shadow is always going to be on the xy plane. And this shadow will be the hypotenuse of my rx and ry, where this angle right here is actually 90 degrees. Okay? And this shadow, which is the hypotenuse of rx and ry, becomes the adjacent component of my r and rz, and this angle here is also 90 degrees, where r is the hypotenuse of sr and rz. Everybody okay with that? This angle here, which is the reference angle, I'm going to call that angle alpha. And the angle from the positive x-axis counterclockwise measured towards the shadow vector is my angle theta. From the positive z-axis to my position vector r, or the resultant, we call that angle phi. All right. So I can represent my r vector now in polar form. So this is obviously Cartesian form. Right? This is the Cartesian form. The polar form for my r vector can be written as the magnitude of my r, comma, theta, comma, phi. This is the polar. Okay? So my alpha is a reference angle, right? Remember, like when we had a vector, like in second quadrant, we had like beta as your reference angle, right? And theta would be all this, right? So if I were to look at the two-dimensional one, and if I had like a vector here, this was your theta, and this was beta with the reference angle. Similarly, from the z-axis, positive z-axis, to your shadow vector will always be 90 degrees. Because this is perpendicular, because this is shadow vector is always going to be on the xy plane. So shadow vector and z will be 90 degrees. So if your z is positive, that means your phi is going to be between 0 and 90. If your z is negative, then your phi is going to be greater than 90, but less than 180. So the key is to find this alpha. So once you find alpha, right, make sure you find it in positive angle. Then if its z is positive, then your phi is 90 minus alpha. If your z is negative, it will be 90 plus alpha will be your phi. Okay, so maybe we can write that down. So if z is positive, right? If z is positive, then your phi is 90 minus alpha. Right? If our z is negative, then phi is 90 plus your absolute value of your alpha. Your alpha is really just tan inverse of RZ over shadow. Okay? All right. Any questions? So this is three-dimensional vectors. And if you want to practice a little more, I guess we can do a little more on this next week when we do cross products. All right. So I'll put some worksheets up there for practice, and I'll put this three-dimensional vector grid so you guys can print it out as much as you want. So you don't have to keep drawing this. So you can just print a couple out, and then you can just follow with me when I do these things. I'll post it up on Schoology after this lecture. So I'll stop the recording for this three-dimensional vectors for now before we start the cross product.